laser in a lab in eastern China is now writing full-color images directly onto bare metal, 10 square centimeters every second, and not one drop of ink ever touches the surface. No cartridge, no nozzle, no pigment at all. Just a beam of light and a sheet of metal that comes out the other side looking like a printed photograph. If that sounds impossible, that's because for the last 50 years, every color printer on Earth has worked the exact same way: squirt tiny dots of colored chemical onto a page and hope they don't fade, clog, or run dry at the worst possible moment. This machine skips all of it entirely. Behind it is a team at Westlake University in Hangzhou, and they are not the only ones racing toward the same finish line. Earlier this year, a completely separate group at Kobe University in Japan solved a related version of the same problem using a totally different trick: coating microscopic silicon spheres so precisely that they could finally be sprayed through a normal inkjet nozzle. Two teams on two sides of the same region, chasing two different methods toward one shared target: killing the ink cartridge for good. Today we're breaking down how a beam of light can paint in full, vivid color without a single pigment anywhere in the process. Why the printer industry has spent decades quietly, depending on you never finding out this was possible. And what happens to a business worth well over $100 billion a year if either of these methods actually works its way out of the lab. To understand why this matters, you have to go back to 1977 to a Canon engineer named Ichiro Endo, working late one night in a lab outside Tokyo. As the story is usually told, Endo accidentally touched a hot soldering iron to a syringe filled with ink. The sudden heat made a tiny air bubble form inside the fluid, and that bubble expanded fast enough to shoot a single droplet clean out through the needle. It was an accident, but Endo recognized instantly what he was looking at: a way to fire liquid ink onto a surface with total, repeatable precision, using nothing but a burst of heat. That accident became the bubble jet, and the bubble jet became the foundation of the entire modern inkjet printing industry. Canon built a business around it. Hewlett-Packard developed its own competing version within the same decade. Printer manufacturers realized something that would define the industry for the next 50 years. Sell the printer itself cheap, sometimes almost at a loss, and make the real money selling the ink required to keep it running over and over for the entire working life of the machine. Ounce for ounce, some inkjet cartridges have sold at prices higher than vintage champagne. Printer companies built entire engineering divisions around locking cartridges to specific regions and specific authentication chips that quietly refuse to function with anything but the manufacturer's own overpriced refills. But here's the part nobody puts on the marketing slide when they sell you a shiny new printer for less than the cost of the ink that comes inside it. The underlying chemistry itself was never actually solved. It was just packaged well. Pigment-based ink fades under direct sunlight over months and years. Dye-based ink, which produces more vivid colors, fades even faster, sometimes visibly within weeks near a window. Nozzles clog if a printer sits unused for too long, and the standard fix is simply buying a replacement cartridge before the old one is anywhere close to empty. Every color you have ever printed exists because a microscopic dot of dye is absorbing certain wavelengths of light and letting the rest bounce back toward your eye, and that dye begins chemically breaking down the moment it leaves the nozzle. Imagine trying to keep a photograph looking vivid for 20 years by quietly repainting sections of it with watercolor every few months and charging the owner premium prices each time. That is essentially the deal every printer owner on the planet has quietly accepted for half a century. So, the real question researchers on two continents have spent years chasing was never really, how do we build a better ink? It was bigger. Do you actually need ink at all? It turns out, nature answered that question a very long time before any laboratory did. A peacock feather contains no blue pigment whatsoever, anywhere in its structure. Neither does a butterfly wing, a beetle's shell, or the shimmering, shifting skin of certain deep-sea fish. Their color comes entirely from physics, not chemistry. Microscopic structures on the surface, smaller than a wavelength of visible light, that bend and interfere with incoming light so precisely that only certain wavelengths bounce back toward your eye while the rest cancel out. Change the size of that structure by only a handful of nanometers, and the color changes completely, with nothing added, nothing removed, and nothing chemically altered in the material at all. This effect is called structural color, and once researchers understood it, an obvious question followed almost immediately. If a butterfly can do this by accident, through millions of years of evolution, Could a machine be built to do it deliberately, on command, in full color, fast enough to matter? Two separate teams, on two sides of Asia, just proved the answer is yes. Go ahead and subscribe now so you catch how they actually pulled it off. Structural color has technically been studied for decades, but reproducing it in full, controllable color at meaningful speed is an entirely different engineering problem. And this is exactly where the Westlake University team's laser enters the picture. Picture a soap bubble floating in afternoon sunlight. It contains no pigment either, and yet you can see swirling, shifting rainbows sliding across its surface because the bubble's film is only a few hundred nanometers thick, and light bouncing off the front surface interferes with light bouncing off the back surface at the exact same instant. Depending on the precise thickness of the film at any given point, certain colors cancel each other out through destructive interference, while others reinforce and intensify through constructive interference. A slightly thicker patch of film gives you a swirl of blue. A slightly thinner patch gives you a streak of gold. The color was never painted onto the bubble. It is built directly into the geometry of the surface itself. The Chinese team's core breakthrough was figuring out how to control that geometry deliberately, with a laser, instead of leaving it up to random chance the way a drifting soap bubble does. They start with an ordinary metal sheet coated in two ultra-thin layers stacked on top of each other. A titanium aluminum nitride layer sitting directly above a titanium nitride layer, each one only a handful of nanometers thick, far too thin to see or feel with your fingers. When an ultra-fast laser pulse strikes a specific spot on that surface, it does not cut, burn, or engrave the metal the way a standard industrial laser marker would. Instead, the pulse triggers an extremely precise, extremely thin oxide layer to form right at that exact point. And the thickness of that newly formed oxide layer determines exactly which color wavelength bounces back to your eye, following the same physics as the thickness of a soap film determining its rainbow. Shift the laser a fraction of a millimeter, adjust the pulse duration by a fraction of a second, and you get a completely different, precisely controllable color with the same durable, non-toxic metal sitting underneath the entire surface the whole time. Researchers working on this technique have started referring to it as an inorganic ink, which is an odd phrase if you think about it, because there is no ink involved anywhere in the process at all. Just focused light, quietly rewriting the physical surface of a piece of metal one microscopic point at a time. 10 square centimeters every single second. That is the current writing speed of the system, and it sounds modest on paper, until you remember this is happening at a resolution fine enough to reproduce a genuinely detailed photograph, one laser-written point at a time, on a material that fundamentally cannot fade the way dye does, for the simple reason that there is no dye anywhere on the surface left to fade in the first place. Meanwhile, on the other side of the region, the Kobe University team took a completely different route toward the same destination. Instead of writing color point by point with a laser, they engineered silicon nanospheres, tiny crystal balls somewhere between 100 and 200 nanometers wide, and coated each one in an ultra-thin silica shell specifically designed so light wouldn't scatter incorrectly right at the boundary between the sphere and its surroundings. Get the sphere's exact size right, down to the nanometer, and it reflects one specific, predictable color through the exact same underlying physics as a peacock feather. Get the coating right, and you can suspend billions of these microscopic spheres inside an ordinary liquid and run the entire mixture straight through a completely standard inkjet printer nozzle, the very same category of nozzle Ichiro Endo's accidental discovery made possible 50 years earlier. No dye anywhere in the mixture, no pigment, just physics, sprayed onto a surface the way ink used to be. What makes this genuinely different from every earlier attempt at structural color is durability under real-world handling, not just in a sealed lab chamber. A pigment fades because light itself is slowly tearing the dye molecule apart, one photon at a time, until the color simply stops reflecting the way it used to. A structural color has no molecule to tear apart in the first place. The nanostructure creating the color is baked directly into the physical shape of the surface. So as long as you don't grind the surface down flat with sandpaper or melt it, the color underneath stays exactly as vivid on day one as it does years later. That single property is why researchers keep circling back to permanent applications first, security features, industrial labeling, currency, rather than the family photo on your refrigerator. So, does any of this mean your printer at home is about to start firing lasers or shooting silicon spheres instead of ordinary ink cartridges? Not yet, and this is the part worth being genuinely honest about before we go any further. The Chinese laser method currently works well on metal and similarly hard reflective surfaces, but not on standard printer paper, which makes it excellent for durable, permanent applications and completely impractical for tonight's homework. The achievable color gamut is also noticeably narrower than what traditional dye-based ink can produce, particularly in certain saturated shades of red, simply because you are working within the hard limits of light interference, rather than freely mixing chemical pigments together. The equipment itself is a precision ultra-fast laser system, the kind that costs as much as a small house, not something that is fitting inside a $200 home printer anytime soon. The Kobe University approach is considerably friendlier toward everyday materials, working comfortably on flexible plastic film and even curved metal surfaces, but its current resolution sits somewhere between 125 and 250 dots per inch, while a typical consumer inkjet printer sold today can comfortably push past 4,000 dots per inch without any real effort. Neither research team is claiming their current lab prototype is anywhere close to ready to replace the printer sitting in your home office right now. What they're actually claiming is narrower, and honestly, far more interesting that the core physical barrier separating theoretically possible from practically impossible for full color. Structural printing has finally, genuinely been solved independently on two separate continents, using two completely different methods within roughly the same short stretch of time. There's also a myth worth correcting here, because headlines covering both papers leaned hard into the end of printer ink, and that framing skips a step. Structural color is not a drop-in replacement you install into an existing printer. It is closer to an entirely new manufacturing category sitting next to inkjet and laser printing, not on top of it. The metal and laser method in particular is currently better suited to industrial marking and anti-counterfeiting than to anything resembling a home office. That distinction matters because it's the difference between a technology that quietly reshapes a handful of specialized industries within the next few years and one that shows up in a big box store next to the printer paper. Right now, this is firmly the former, even if the long-term trajectory clearly points toward the latter. Zoom all the way out, and the stakes here go well past whoever ends up printing your birthday cards a decade from now. A global printer industry worth well over $100 billion a year has been quietly built on the simple assumption that ink always has to run out eventually. Every region-locked cartridge chip, every artificial print count restriction, every "your ink is critically low" warning that pops up while the cartridge is still genuinely half full exists because the underlying business model depends entirely on repeat purchases, not on the printer itself actually lasting as long as it physically could. Structural color removes that dependency completely, from the ground up. A surface colored through geometry instead of chemistry does not fade under sunlight the way dye reliably does not dry out inside a clogged nozzle, and never needs refilling, because there is nothing sitting inside it that can ever run out in the first place. That has obvious appeal for anyone tired of paying more per liter for printer ink than they would pay for a decent bottle of wine. But the implications run even deeper for entire industries that care far more about permanence than about everyday convenience. Currency and passports already rely on structural color tricks specifically to fight counterfeiting, because a color built directly into physical geometry is dramatically harder to fake convincingly than a color simply mixed from ordinary dye. Packaging companies are reportedly watching this research closely, since a non-toxic, non-fading coating could eventually replace pigments that currently end up as microplastic and chemical waste in landfills and waterways around the world. Even the display industry has one eye on this space, since a surface that reflects specific colors using nothing but ambient light in the room is essentially the same underlying idea behind today's low-power reflective e-paper screens. Textile manufacturers are watching too, since fabric dyed with heavy metals and synthetic chemicals is one of the more polluting steps in modern clothing production, and a woven fiber that gets its color from geometry instead of chemistry would sidestep that problem almost entirely. And China and Japan are far from the only labs chasing this particular breakthrough. Research groups in the United States and Russia have published their own separate versions of laser-written structural color over the past several years, with some pushing achievable resolution even higher through slightly different metal nanostructure combinations, which tells you this is not a single company's private secret project locked away somewhere. It is a genuine, active international race, with multiple governments, universities, and private labs all treating pigment-free, physics-based color as a technology genuinely worth owning first. Which quietly raises the one question nobody currently inside the printer industry seems especially eager to answer out loud. If a technology exists that never needs refilling, never meaningfully fades, and never locks a customer into repeatedly buying one specific brand's overpriced cartridges again, does an industry whose entire profit model depends on the exact opposite of all three of those things actually want to see it succeed anytime soon? Or does structural color quietly end up like plenty of promising lab breakthroughs before it, technically solved years or even decades before anyone holding the actual market power to sell it decides it has finally become convenient enough to let the rest of us have it? That tension between what is now physically possible in a lab and what remains commercially convenient for the handful of companies currently selling you ink at premium prices is really the entire story sitting underneath this one. Two research teams on two sides of Asia, working independently and without coordinating, just proved within months of each other that vivid, lasting color does not actually require a single drop of chemistry at all. What happens from here depends far less on physics, which has clearly already been solved, and far more on whether an industry that quietly built its entire business model on ink eventually running out is in any real hurry to make that model obsolete. If you want to catch the next deep dive into breakthroughs exactly like this one before almost anyone else does, go ahead and subscribe now, and tap the notification bell so you genuinely don't miss it the moment it drops. Here's the question worth sitting with for a minute after this ends. When the underlying technology to kill printer ink forever already exists, quietly proven in two separate labs on two separate continents, is it actually consumer demand that decides when the rest of us finally get to use it? Or is it the handful of companies still profiting enormously from the cartridge sitting in your printer right now? We'll be back again soon with another story pulled from the edge of what China and its neighbors are quietly building next.